Hi, and welcome to a lecture on polarization. Polarization refers to the orientation of the electric field vector as a function of increasing distance along the path of propagation, or, equivalently, as a function of time at a fixed point in space. Note that polarization refers to the change in the electric field vector's orientation as a function of either time or distance. There are generally three broad classes of polarization. First, linear. Linear refers to a constant orientation of the electric field vector with respect to distance or time. Circular refers to an electric field vector which is rotating with distance or time. An elliptical is a general case which includes the linear and circular special cases. Let's begin with linear polarization. In these two figures, I'm showing two examples of linear polarization. In the first example, I'm showing an electric field vector which lies entirely in the xz plane. So the electric field is always in that plane, and the electric field vector orientation can change, but it never moves out of this plane. In this formulation, we could describe that as being x hat times some complex valued constant times e to the minus j beta z, indicating that the wave is traveling in the plus z direction. Similarly, I could have a wave in which the electric field vector remains in the yz plane, as shown here, in which case the electric field would be y hat times some complex valued constant times e to the minus j beta z. Note, in both of these cases, the electric field vector remains in the plane. Its direction can change only by a sign, and we refer to this as linear polarization. Now, we can generalize this a little bit. We could say the electric field intensity is in some other plane, maybe not xz or maybe not yz, but perhaps any of those planes in between. In which case we have x hat cosine phi sub p plus y hat sine phi sub p, or we could refer to this as being rho hat, a vector which points in the xy plane in some direction. So we could refer to this electric field as being rho hat E naught, again, some complex valued constant, times e to the minus j beta z, for some value of phi sub p indicating the angle at which that electric field vector is tilted. Now, we must be very, very careful. I've indicated here that this is rho hat, and it is a physical vector pointing in some direction in the xy plane. You may not generalize this as indicated here, where we have x hat times some complex valued constant plus y hat times some complex valued constant, unless those two coefficients have the same phase. If this is not true, then we will not have linear polarization, as we will demonstrate later in this lecture. So some examples of linear polarization. First of all, dipoles exhibit linear polarization. Here's a dipole. The currents are along the dipole, and as a result we get a wave whose electric field vector remains in that same plane. Also, certain patches, not all patches, but certain patches also exhibit linear polarization. And that occurs when the radiation due to the patch can be represented as currents along opposite sides, in which case we once again get an electric field vector which remains in a plane. So these are all examples of linear polarization. Circular polarization. One way to see what circular polarization is to begin with linear polarization and then make one modification. Once again, for a dipole, this is linear polarization. The electric field remains in this plane, which contains the axis of the dipole. In fact, as drawn here, you might refer to this as being vertical polarization. And you could also take a dipole and rotate it 90 degrees, as shown here, in which case you would get the electric field vector in this plane, and you might refer to this as horizontal. Now, if these fields are added in any particular way, we still get linear polarization because the electric field remains in a plane. If we shift the phase of the second dipole by 90 degrees, that's pi over 2 radians, we get a different result. What happens is if we shift by 90 degrees, the first dipole will completely account for the field at this place along the path of propagation. And the reason is because we'll have a 0 here. The second dipole will account for the electric field in this position because the field from the first dipole will be 0 at that point. So phase shifting one of the dipoles by 90 degrees causes a situation where we see the effect of the first dipole here, and where there are zeros in the field from the first dipole, the second dipole is contributing this other field in the orthogonal direction. So now if we try to trace the path of that electric field vector as it propagates, we see that spiraling around. In fact, here is the picture you should have in your mind when you think about this. The tip of the electric field vector is following a path which is corkscrewing through space, as shown here. Similarly, at any point in space, we should see this corkscrewing behavior, and we do. If we sit at one location and we observe the electric field go by, we will see the tip of the electric field spin around in place as indicated here. And we'll note that this traces out a circle, and it rotates clockwise in this case because of the particular choice of phase shift that we made here, plus 90 degrees. So when that horizontal dipole was phase shifted by plus 90 degrees, then we get this particular direction of rotation for the tip of the electric field vector. And we refer to this as left circular polarization, or LCP. Now, one way to quickly identify LCP is using your left hand. If you take your left hand and you point your thumb in the direction of propagation, and then you see which way the fingers of your curled left hand point, they will point in the direction that the electric field vector rotates. And that's left circular polarization. This is sometimes referred to as left hand circular polarization for reasons you can now understand. So you might see this abbreviated LHCP, but it means the same thing. Now there's a mathematical version of this, if you prefer, and that's simply to look at the two dipoles. Here's the electric field from the first dipole. Here's the electric field from the second dipole. Here's that 90-degree phase shift, represented here as the factor J. And now we can just work through this. We can represent E naught, a complex valued constant, in terms of its magnitude and its phase. And similarly over here, we can represent J as e to the plus j pi over 2, and E naught in terms of its magnitude and its phase. And we can combine factors in the exponent, as shown here. And then to see what the field actually looks like, the real valued physical field, well, we take this electric field expression, the one shown here, which is a phasor quantity, and we can convert it back to this real valued physical field by multiplying by e to the j omega t, and then taking the real part. When we do that, we see x hat, magnitude of E naught, times this cosine function for the first dipole, and y hat, magnitude of E naught, cosine of this argument. And we see that the cosine of the second part is phase shifted by pi over 2. So we get the result that we obtained previously just by visual inspection. So one advantage in looking at the mathematical version is we get one additional little piece of information. That's if we go back to the original phasor expression, this one, we note that we can combine these two terms together to obtain this factor out front, this vector expression, x hat plus jy hat. Well, recall, if this thing was either x hat or y hat, that was linear polarization. But for circular, we have x hat plus j y hat. So this is an orientation of the electric field vector in complex space. X hat is pointing in one direction, and y hat is multiplied by j. So this is a direction in complex space. Now, don't let that blow your mind. This is merely a way of describing a time-varying orientation as a constant but complex-valued quantity. So just as a phasor is a constant which represents a sinusoidal waveform, this vector expression is a constant direction which represents a rotating field vector. Right circular polarization, or right-hand circular polarization, can be obtained in the expected way, and that's simply by changing the phase of that second component. So instead of going plus 90 degrees for that second dipole, we go minus 90 degrees, and that causes the vector to rotate in the opposite direction. In other words, right circularly polarized. So everything I said about the left-hand circular polarization and the left-hand rule for determining or identifying left circular polarization now applies to right circular polarization and right-hand circular polarization. So, how do we get left circular polarization or right circular polarization? Well, as we just showed above, we can do it with two dipoles. We put them in an orthogonal orientation, and we feed one of them 90 degrees out of phase with respect to the other one, and we will get that circular polarization as we just demonstrated. This can also be done with patches. The way you do it with a patch, or one of many ways you can do it with a patch, is to feed the patch using a pin that's off-center with respect to the outline of the patch. This will create linear currents along one edge and linear currents along the opposite edges that are 90 degrees out of phase if you select that geometry correctly. And once again, you will end up with a circular polarization for exactly the same reason that you saw it in this case. And once again, this is not the only way to generate circular polarization with a patch. There are other ways. And furthermore, there are other types of antennas that create circular polarization, such as helix antennas. At this point, a warning, and that's that the definitions of left circular polarization and right circular polarization that I've shown here are the usual ones. Now, when I say usual ones, they're the ones that are mandated by IEEE standards documents. They are also the definitions used by the IAU, the International Astronomical Union, which sets these standards for radio astronomy. And they're also the ones that show up most often in quantum physics, where this phenomenon is sometimes addressed. However, it's not the only definition, and these definitions can be made in exactly the opposite way. And by the opposite way, what I'm saying is that when we came up with these definitions, we considered the source. In other words, it's left circular with respect to the source, and it's right circular with respect to the source. But you could also look at it from the perspective of the receiver. And if you think about what the receiver sees, then those definitions are exactly opposite. So left circular and right circular polarization can be defined in completely the opposite way. And when you're doing that, you're defining it with respect to the receiver. And this is not an unusual thing. It's quite common in optics, in photonics, and SPIE has a standard definition in this way. Now, fortunately, these apply primarily to light wave applications and not radio applications. Nevertheless, you should be aware that left circular and right circular polarization can be defined in two completely opposite ways. And if you're not aware of that, you could potentially be confused, so you should always check. Now I'd like to talk about elliptical polarization. And as an introduction, let's consider the following expression for the electric field intensity. In this expression, we are once again describing a wave traveling in the plus z direction. And now we have x hat ex plus y hat j ey. Note the j there. And also note that I'm requiring EX and EY to be real valued. So this is guaranteeing that 90-degree phase shift. From the preceding discussion, we know that if either EX or EY is 0, we're going to end up with linear polarization. For example, here we might have just EX and 0 EY, in which case we know the tip of the electric field vector is going to go back and forth in a plane. Alternatively, the values of EX and EY might be either equal or opposite in sign, in which case we end up with left circular polarization or right circular polarization respectively. In this case, the electric field vector is rotating either this way or in the opposite direction, but it's tracing out a circle. Now the general case is when the magnitudes of EX and EY are not equal to 0 and also not equal to each other, in which case we end up with elliptical polarization. We see that the tip of the electric field vector is rotating, but it isn't following a circle, it's following an ellipse. Furthermore, you can see that elliptical in the extreme can be either linear polarization or circular polarization. The special case where the semi-minor and semi-major axes are equal is circular polarization, whereas the case where the ratio of these axis lengths is infinite, we end up with linear polarization. Elliptical polarization is usually not desired. This usually is not a desired polarization state, but it is common nevertheless, and it's common because antennas, which are intended to produce left or right circular polarized radiation in the direction of maximum directivity, typically produce a different polarization, namely elliptical, in other directions. So as an example, here's a right circularly polarized patch, which in its most directive direction, the direction in which the directivity is greatest, we get pure right circular polarization. But in other directions, away from that nominal broadside direction, but which are nonetheless usable and used for the application, we end up with impure circular polarization, namely elliptical polarization. In fact, it is quite likely that as you get farther and farther away from the broadside direction, the closer and closer this is going to be being linear polarization. So, to quantify this, we come up with this term axial ratio. And the axial ratio is the ratio of the magnitude of the electric field along the major axis of the ellipse to that along the minor axis of the ellipse. So, we end up with an axial ratio of 1, that is 0 dB, for circular polarization, and larger values for elliptical polarization, 1 up to infinity, and when the minor axis shrinks to 0, we end up with linear polarization. So the axial ratio can be used to describe a polarization state ranging from pure linear to pure circular. And once again, the typical situation is that the axial ratio will increase as you move away from the nominal direction. So for this right circular polarized patch, we get an axial ratio of 1 in the broadside direction, and then increasing axial ratio as we move away from broadside. Finally, in this lecture, let's talk about how to choose polarization. In other words, from the perspective of a systems engineer, what might you deem to be appropriate as the polarization state for the antennas on the two ends of a link? So, to discuss this, here in this column is the polarization state of station 1, one end of the link, and then polarization of the antenna on the opposite end of the link, station 2. And the first possibility we might consider is linear to linear. In other words, maybe we have dipoles on each end of the link. Well, this is hard to avoid in some applications, namely terrestrial applications at frequencies in the UHF range and below. And this is due to the proximity of the ground, and not merely that the ground might be close, but that the ground might be electrically close. So if the ground is within a few wavelengths, it's very difficult to avoid using either vertical polarization or horizontal polarization. And furthermore, circularly polarized antennas at these frequencies tend to be large and awkward. For example, if you need two dipoles, well, that's a lot bigger and more awkward at these frequencies than a single linear antenna. Now, if you're not operating in terrestrial applications and frequencies in the UHF band or below, then linear to linear is not a particularly attractive choice because it requires good alignment between the dipoles on each side. Just to show you an extreme case, if you have vertical on one end and horizontal on the other, there will be no received power. But even if you're off by 45 degrees instead of 90 degrees, there will be a pretty significant penalty in received power. So, in general, we'd like to find polarization choices that do not entail this reduction in power due to unavoidable misalignments in the antennas. So a choice that goes in that direction is going circular to circular. This does not require good alignment. Those antennas can be rotated. It only requires that they have the same sense. So left circular on both sides or right circular on both sides. So because this is insensitive to alignment, this is common for satellite communications when the satellite's communicating with the ground. And that's because it ameliorates this problem that the satellite might be rotating with respect to the direction to the ground station. And therefore we can tolerate that with no loss of power. So this choice is common in satellite communications. It's also common when you can put the antennas way far up, high up in the sky, and away from the ground, and then you have a similar advantage. Another choice might be circular to linear. This is useful when one side is a device that is design constrained to be linear polarization. So for example, perhaps you have a wireless sensor that needs to be super tiny, and the only way you can accomplish that is by having a linear antenna. Well, you don't know how that linear antenna is going to be oriented, so one way to deal with this is to have the other end of the link be circular. Now this entails a 3 dB penalty in received power, going from circular to linear, but on the other hand, the penalty due to misalignment will not be greater than 3 dB. So it's a compromise. You give up 3 dB of power, but in return you know you'll never lose more power than that because of a misalignment. So you would see such a scheme in sensors communicating with some kind of access point, for example, maybe in some wireless telemetry application or some Internet of Things type application. And also you might see this in some RFID applications, where the tag is linearly polarized, but the access point might be circularly polarized. And then for completeness, let me identify one other possibility, and that's dual linear, doing both, for example, vertical and horizontal to a linear antenna. Now this is addressing a similar problem as identified above, but it avoids the 3 dB penalty on receive, because if you transmit in both polarizations, then linear polarization will be able to receive some combination of those two, so there will be no reduction in received power. The penalty comes in on the transmit side, where you have to transmit twice as much power because you need the same amount of power in both polarization to prevent the power loss on receive. So this is actually quite common. You see this quite often in wireless LAN applications and in cellular telecommunications, where there is transmission in both polarizations, well supported by modern technologies such as MIMO, where you have lots of antennas, so you can have lots of polarization states. And then it accommodates a simple handset, which might just have linear polarization. I'll also point out that some FM broadcast transmitters follow this scheme, where the transmitter produces both vertical and horizontal, so that the orientation of a small, perhaps electrically small, linear antenna can receive that signal without degradation due to orientation. That concludes this lecture on polarization.